Hello, everybody. Our speaker today is Adam Chapman from the Academic College of Tel-Aviv-Yaffo, and he will be talking about measuring the associativity of loops. Adam, please go ahead.
So thanks, Elad. I'll try to share my iPad. Just a second. So it's advanced. This thing. Okay, so far so good. Okay, so hi everybody. Um, I must begin by saying that this is not really my talk. My PhD student Ilan Levin was invited to give a talk about his own paper, which he has full credit for. But since you know the situation in Israel is rather complicated, he's preoccupied with other things. I was asked to give some outline of the main idea behind this talk, and I'll try to do my best. It's going to be rather short, and I'll mostly stick to the main things, the main theorem, and the idea around it and behind it. So I'll just add that Ilan is currently my joint PhD student with Uzi Vishna from Bar-Ilan University. He was our master student, and in between those two degrees, he took some time off, and instead of going to the beach and have some good time, he decided to work on his own problem, and then he wrote it down, published it, and this is the paper that he was going to talk about. Published last October, I think. So the title is Measuring the Associativity of Loops. But before we talk about loops, let's talk a little bit about groups. So if you are given a group, let's say you don't know what the group is, but you know that it's a finite group, but very large, and you want to know whether it's abelian or not. So for instance, if you are trying to decode something and you have some group behind the code, it might be helpful to know if it's abelian or not. And suppose you can sample a bunch of commutators. How many commutators do you need in order to guarantee that it's abelian up to the probability of 99.19%, for instance? So if you know that for a non-abelian group, you don't have so many non-trivial commutators, it might help you. It might reduce the number of samples that you have to take, of the amount of tests that you have to carry out. So there's a famous theorem in group theory about this question, and the theorem is this. I don't even know who to attribute this to. This is rather classical, but let's just call it a theorem. You have G, a finite group, and you suppose that it's non-abelian, and you take a pair XY from G cross G uh, with the uniform distribution. So you pick a pair X comma Y from G cross G randomly. So every pair has the same probability of getting chosen. And you ask yourself, what is the probability of XY to be equal to YX? The theorem states that this thing is no greater than 5 over 8. So it's a rather strange theorem. But then if you have a non-abelian group, if you checked like 12 different commutators and they're all non-trivial, then obviously it's not abelian. But if they're all trivial, then you might have a very good chance of the group actually being abelian because of this, because you expect not much more than one half of the pairs to have a trivial commutator. So this theorem has a rather easy proof. So how does it go? So this group is non-abelian. If you ask yourself what is the chance of xy to be equal to yx, then it breaks into two options. If x is central, then that's fine. So let's denote the center of the group by z. So what is the chance that x is central? And then it doesn't really matter what y is. So you multiply it basically by 1. But then you should add also the probability that x is non-central times the probability that y commutes with x. So y is in the centralizer of x inside the group, given that x is non-central. So that's essentially what we need to compute. Now, let's think about this formula a little bit. So one thing is that the moment x is non-central, you have some element which does not commute with x. And then if you take the centralizer of x inside the group and you multiply the centralizer by that element, you have another set of elements in which no element commutes with x. So the chance that y is in the centralizer of x doesn't exceed 1/2. So it's always less or equal to 1/2. Now, for this guy, if this is t, this is 1 minus t. So clearly, the larger this guy is, the smaller the other one is. But the first one is multiplied by 1, and the other one is multiplied by a number which is no greater than 1/2. So obviously, the sum is less or equal to the case where the first one is the maximum it can be. And that again happens no more than 1/2 of the times because the center is no more than 1/2 of the elements of a non-abelian group. So this whole thing is at most 1/2 plus 1 minus 1/2, which is again 1/2. I made some, no, it's not. I made some mistake. I made some mistake in this computation. I'm a little bit embarrassed. Hmm. It's not supposed to be difficult. Well, I apologize. I eventually it should be something like 1/4.
Adam,
Yeah,
the center cannot have index 2, right? So it has to be smaller than 1/2.
yeah. Perhaps it's 1/4 plus 3/4 times 1/2. Yeah. So yeah. So okay, you're right. So it has to be something like at most 1/4 plus 3/4 times 1/2. And then it's like 2/8 plus 3/8, which is 5/8. Yeah, okay, you're right. So the thing is that the argument is correct, but just the center cannot be more than 1/4 of the group. So the size of this guy is at most 1/4 the size of the group, if the group is non-abelian. Anyhow, that's a classical theorem, and it's probably correct what Solly mentioned, that this is the key to get this upper bound. Now, there are some groups that actually show that this bound is sharp. If you take, for instance, G to be Q8, which is the group of quaternions, this group contains plus minus 1, plus minus I, plus minus J, and plus minus I times J. So I and J are the famous quaternions. So you have I squared equals J squared equals -1. And J times I is simply negative I times J. So it's a group that contains 8 elements, and these elements also generate the quaternion algebra if you work over the reals, but just as a multiplicative group, that's what you get. And if you compute it here, then really the probability of a pair xy to have a trivial commutator is indeed 5/8, because here the center is exactly 1/4 of the elements, and if you pick a non-central element like I, then its centralizer is exactly 1/2 of the elements, and you get the desired upper bound, which is 5/8. There are other examples. For instance, if you take the group of the symmetry group of 3 elements, then here the probability of commutator to be trivial is actually smaller than 5/8. It's exactly 1/2. And this question of what kind of probability you can get here, it's an active field of research. There's apparently not a finite number of options, but if you ask how many options you have above a certain number, then this number is probably finite, at least down to something like 1/4. I don't remember exactly the numbers, but not every number is possible, and even below 5/8. But 5/8 is the optimum. So that's the rather classical question about groups. Now, when you switch from groups to loops, you lose associativity. And you can ask similar questions. So first of all, you can ask the same question exactly. What is the chance that a given pair xy has a trivial commutator? And here it depends on what kind of a loop you're looking at. Loops vary quite remarkably in terms of structure. So they have a less rigid structure than groups. But you can also ask about the associators. What is the chance that a random associator is trivial? And here, again, you have loops. They form a too large a family. So you need to shrink it down to something that you can really work with. And the theorem that Elon proved is the following. So this is Levin's theorem from 2025. And what he stated is this: if L is a Moufang loop, I'll mention briefly what a Moufang loop is in a second. With nuclear commutators, I'll mention what that is too in a second. Then if you take x, y, and z from L times L times L chosen uniformly, then the probability of the commutator x, y, z to be trivial is at most 43 over 64. So here again, if you have a loop satisfying these conditions, so it's a Moufang loop and it has nuclear commutators, the number of random associators that you need to sample in order to decide quite positively that it's actually a group and not a loop is not as big as you expect, because you don't need to, it's just enough to know at a very high probability that more than 43 over 64 of the associators are trivial. And then it automatically goes up to 100%. So that's the theorem. I'm not going to prove the entire theorem, but I am going to give an example, and I want to explain what the conditions mean. So first of all, what is a Moufang loop? So for those who study alternative algebras, especially people who study Octonions, they're quite familiar with the Moufang identities. So for the Octonions, and I think also for any alternative algebra actually, if you pick any x, y, and z, then they satisfy the following funny conditions. So if you have x times yz times x, then this thing is equal to xy times zx. And if you have x, y, xz put in this way, then it becomes x, y, x times z, and also the opposite of that. So you have x, y, x, z. Then this guy is z times x, y, x. And in particular, every two elements satisfying these conditions, if you have a loop satisfying these conditions and you pick only two elements, then they generate a subgroup. And more particularly, if you choose one element, then this element is power associative, so it doesn't matter where you put the brackets. It's going to turn out to being the same thing. So Moufang loop is what you take if you take these Moufang identities from alternative algebras and you impose them on loops. In particular, if you start with an alternative algebra like the Octonions, and you pick only the generators, let's call them I, J, and L, then they generate something which is closed under multiplication. That thing is a loop. It's not associative, but every element has an inverse, and it satisfies the Moufang identities, so it's a Moufang loop. I'll write down the example explicitly in a second. So when we say Moufang loop, we mean that it satisfies the Moufang identities, and the moment you have these identities, you can talk about commutators, because the moment you don't have the fact that every two elements generate a subgroup, then what is a commutator? It's also a question. But if x and y they live inside a subgroup, then you can talk about the commutator of x and y. And then when you say commutators are nuclear, you mean that they live in the nucleus of the loop, which means that the associator of three elements in which one of the elements is a commutator must be trivial. So if you have I'm talking about nuclear commutators. So if you have x is the commutator of some a and b, then the associator of x, y, and z is always trivial. So x, y, z is always equal to x times yz for any choice of y and z. So these two assumptions, they look a little bit artificial perhaps, but then again, you want to capture something that you can work with, because otherwise loops are just too wild. And I wouldn't dare saying that most loops satisfy these conditions, but at least one interesting loop satisfies these conditions, and that's the loop that you get from the generators of the Octonion algebra. So Elan's upper bound is 43 over 64. Now let's just take this one example and see how we get there. One example is what we call O16. So it's generated essentially by I, J, and L. So these are the three generators of the Octonion algebra. I'll write explicitly the elements. We have plus minus 1, plus minus I, plus minus J, and plus minus I times J, but you also have plus minus L, plus minus IL, plus minus JL, and plus minus IJL. And I can also remind you what the Cayley-Dickson doubling formula gives for the octonions, but here it's really you don't really need to go over all the details, but it's a fun fact that if you take IJ times L, then it's negative I times JL and some other funny things that happen for this specific loop. But it is a Moufang loop. It is Moufang because all these elements, they live inside an alternative algebra which satisfies the Moufang identities. And all the commutators here are plus or minus 1. So the moment the commutators are plus or minus 1, the commutators are central, and central also means nuclear. So it has also nuclear commutators. So it's Moufang and nuclear commutators. And if you try to calculate the probability that a given associator is trivial, then that's how it goes. What's the chance that x, y, z is equal to x times y, z? So here again, you have the tree breaks into three branches. One is when x is central, so x is plus or minus 1. The other is when x is not plus or minus 1 or minus 1. And then the question is, what about y? If y in this case is plus minus 1 or plus minus x, then it doesn't matter what z is, because then y and x are basically coming from the same subfield. If y is x, it doesn't matter. If it's negative x, it still doesn't matter. And then z, it belongs, then y belongs to the same subgroup generated by x and z, no matter what z is. And then the associative is trivial. So in this case, the moment y belongs to this very small subgroup of O16, then it really doesn't matter what z is. So we can multiply by 1. And the last bit, I'll write it, okay, I'll write it here. The last bit is the chance that x is not plus minus 1 and y is not plus minus 1 or plus minus x. And then z, in order to have a trivial associator, it must belong to the subgroup generated by X and Y. Otherwise, the associator becomes -1 because of the structure of this specific loop. So Z has to belong to the subgroup generated by Y and Z. Okay, so that's the computation that we need to carry out. And now the chance that X is plus or minus 1 is 2 out of 16. I have to finish soon. Okay, I'll finish soon. I'll just write the computation and then I have to finish. It's 2 out of 16. The chance that is not, it's 14 out of 16. אני שמעתי, אני מסיים. אני עוד שנייה מגיע. And then the chances that Y belongs to this guy is 4 over 16. And the last bit is, so the chance that X is not this is 14 over 16, which is again just 7 over 8, times 3/4. It's the chance that Y is not what we want. And the last bit, the chance that Z is in this subgroup, the subgroup occupies half of the loop, it's 1/2. And if you add everything, then you get 43 out of over 64. So that's the example that shows that Ilan's upper bound is sharp, and now I have to run to the shelter, so excuse me. And thank you, guys.
Okay, thank you, Adam. Okay, thank you, Adam, for the talk, and I suppose we'll continue next week. Okay. Bye.